So as you can see, more fun stuff from eBay. Here is a, this is a Keithley 168 auto-ranging digital multimeter. It's only 3.5 digits, I believe. But, so what happened is I have two multimeters which I really trust. I have a Fluke 79.3 and I have my, I had a Fluke 77. And my Fluke 77 recently decided to quit working on me, and I'm not too sure what's going on. I may try and repair that, and that may be a video in the future. But anyways, I've been kind of, I wouldn't mind a bench multimeter, just because, you know, basically you get nice bright LED displays, at least if you buy the right one. So, kind of been poking around on eBay. I've actually bought a couple of them. This one was, you know, it's only 3.5 digits, but it was also only $40, so I'm not complaining. It appears it has a battery. Also appears the buttons are a little stiff. Anyway, you know, it's just a cute little box. So, I may have to do some work internally. In fact, I'm pretty confident I will. So as you can see, the guy who shipped this, yeah, apparently didn't put enough packing on there and the handle cracked. But that honestly doesn't bother me that much because it's pretty much never going to leave my bench, I think. So, it looks like it seems to work to me. So that's DC volts. So I think that's saying it's out of range. DC volts, AC volts. I'm not sure if this is true RMS, but we'll see. It's got a battery in there, but it appears it doesn't work off the battery at all because it's supposed to be on the battery right now. So, it may have to be charged. It feels like it's got a lead acid. You can also see these buttons have some issues. There it goes. So we'll have to look. I'll have to look into that. But let me go like that. So that is 9.1 volts. That seems to work fine. So one of the things you can see is this has 2 ohms ranges. It has high and low. And what this actually does is the low only uses 0.2 volts, basically for measuring, and the advantage of that is that it doesn't bias on semiconductors, so you can do in-circuit measurements. I'll have to see about the utility of that, but it's an interesting idea. You know, the downside, of course, is that you're going to lose on, it's not going to be quite as accurate. There's some 10 meg resistors, that should be a good test. Yeah, 10 mega ohms. Yeah, and it's out of range on the low range, because it can't measure the current from that. So I guess when it flashes, it's saying open circuit. So it looks like it doesn't actually have an ohms range, it just uses kilo ohms and mega ohms. That's kind of it. So it basically has 2 ranges. That's kind of amusing. Let me actually grab like a 400 ohm resistor. That's 100 ohms. That should be 0.1 kilo ohm. So you can definitely see it. The auto ranging is rather slow. But these are 1% resistors, so it's within tolerance. It may need to be calibrated. I want to buy one of those DMM checks. Yeah, so they're all measuring about an ohm high, which is very unlikely. Well, actually, okay, so it looks like there's probably about an ohm in my test leads. So it looks like they're all reading about accurately. So that's cool. That's interesting. So it looks like we actually get more precision at low. That makes sense. 1.008 or 0.1008 kilo ohms, so that's 100.8 ohms. definitely am not a fan of the flashing when unconnected. That's very distracting. I can't just leave it on and like Fluke's display, over limit, which is nice because it tells you what it is without, being distracting. I might see if I might try and modify that. Alright, anyways. So now the thing everyone I'm sure most wants to see, which is the internals. So let's turn it off. So you may have noticed, but it's got like the cord wrapped around on the bottom. Actually, that's a pretty interesting printout. So there's like the tolerance. To open instrument, disconnect line cord, loosen 4 screws this side. Hold instrument together and turn over, remove top cover. Additional information inside. Oh, that's cool. So there's your accuracy specs. And it looks like 1, 2, 3, 4 screw. This looks like a little tiny O-ring that fell out of something. I'm not sure. Off, turns instrument off. Line, operates instrument from AC line. Charge, operates instrument from AC line while fully recharging instrument in 12 hours. Inoperative without 1688. And bat operates instrument over 6 hours from fully charged 1688. Inoperative without 1688. So 1688 is presumably the battery pack. Actually, that's an interesting test. Does it come on in charge mode? So it looks like I don't have the battery option. Because if I had the battery option, it should come on when I put it in charge mode. Which is fine. I don't need it, don't really want it. I guess I already have several handheld digital multimeters, so. Here's the interesting bit. It looks like I do have the 1688A option. It's just so grossly discharged, it's not during jack. Also, what is that? It looks like another battery pack. How slow fuses. Interesting. Let me move the camera and we'll continue. So anyways, here's the inside of the multimeter. You can see there's a number of fuses. These look like they're for the multimeter section. This whole thing is, oh look, oh I see, it sits over the screw pedestals. So you can see that that's where the screws are. So this should just lift off. And there we are. So this looks like this is using, it's NiCads, and then there's whatever this is. Okay, so we have 7 cells, 1.2 volts, 2 amp hours, which are these. And we have one assembly, 16.8 volts, 2.25 amp hours, which is whatever this is. So this is presumably, this is 16.8 volts, whereas this is going to be 1, 2, 3, 4, 5. So that's going to be 6 volts. So that's going to be 8.4. This is an 8.4 volt pack. This section is an 8.4 volt pack, and then this section is 16, so apparently it's got twice the cells. Not the little pop turrets. There's not much here. It's basically just straight up batteries. I wonder why it doesn't run when you're connected to that. Anyways, so here's the internals of the actual multimeter. So you've got a shielded section for the analog. Oops. It looks like this just more or less, oh. So this just more or less just sits here and it's actually retained by some little O-rings. If you look there, you can see that there are O-rings slipped over those posts, which are what hold those on. So that O-ring that fell out looks like it came from this corner post here, which is no longer there. The one thing of interest is you can see that they're using a dip socket as the connector for the front panel. They're using one of these, you know, what is it? It's a ribbon cable to dip wire, you know, cable leads, and then they just plug into a dip socket, and that's the interconnect to the front panel, rather than using excuse me, rather than using like a 0.1 inch pitch IDC connector or anything, which is kind of amusing. So you can see we have, that's interesting, jumper wire. That's probably the processor. It's an AMI 7913BX. Line transformer. It's probably a pass transistor or voltage regulator. This is a 2000 mics at 25 volts. And these are line selector switches, which are recessed into the case so you can't easily access them. So, one thing of note is some of these interesting capacitors with color banding on them. These, I'm not sure, I'm not sure what composition they are. They're probably film caps or something along those lines, but the color banding indicates the value rather than printing it onto the cap, which is kind of interesting. Another thing is it looks like at least part of this has been conformally coated. If you kind of look at the shininess of the ICs, it looks like this section's been conformally coated. One interesting thing is you can see, if you look at this disc cap, it looks like this was only partially submerged when they dipped it, because you can see there's conformal coating on that section and not over there. You know, and then we have more of these interesting capacitors, color banded capacitors. And then there's some interesting stuff in there. I think those are 4-lead Kelvin connection resistors. Let's see what's holding this on. So now, if we flip over, so we can see some interesting stuff. So it turns out I probably didn't need to remove it from the case, because it turns out there's just little, very stiff spring retention clips, it looks like. Well, maybe I will have to, because it looks like there's a screw there. Just not sure what it goes into. So this here is a little metal spring clip that wraps around and makes contact with the metal cover on the bottom of the board, or on the bottom of the case, excuse me. Oh, I see, it screws into that. What just came? So here, it actually looks like I didn't have to remove that screw entirely, is the high impedance stuff. It's very interesting. It looks like that is a, I don't know what the hell those are. Let me just quickly start that screw back in there just so I don't lose it. So here is our input section, and this is quite interesting in that you can see that our input matrix switching looks to all have been hand soldered on the top of these switches, you know, presumably for high impedance construction. And then you can see we've got some hand formed resistors. Hand formed resistors running, you know, down to various nodes in this circuit. One thing you can see here is if you see this trace loop here, that's a shielding trace loop to prevent or reduce leakage across the board surface. Over here we've got a little polystyrene axial lead capacitor, some other caps and resistors. This is all, you know, it looks like it's been hand soldered. We have these devices, which appear to be glass encapsulated something. They're labeled JFD 7908 VC32. VC32GNY. I'm not too sure what these are. It looks like they have adjustment holes. If we look, if we look over at that end, there appear to be screw threads down in the hole. So those may be tuning caps of some sort for, you know, I'm not sure how the ADC in this works. It may be dual slope, something like that. It's probably earlier, because this is pretty old. You can see here we have a row of little transistors, and look at how one of the legs is bent out and brought over and soldered into that hole. That's quite interesting. We got a little more tuning potentiometers. You know, this is presumably a big high precision specialty resistor. Actually, that's interesting. If we look, if you can make out some of the texture. So this looks to be like it's presumably it's ceramic, and then they deposit a resistive element or resistive material on it and trim it somehow. I don't know if this was laser trimmed, it may be too early. But, you know, and then you have other stuff here. Here's a really large resistor. That may be the resistor for the AC amps. That is 1 ohm. So I would bet that this is the AC amps current sense resistor. And then that's probably the milliamps. So you have amps and milliamps presumably for those two. And then this little cable here, I'm not entirely certain. There's a fair amount of stuff on the front panel. You can also see that they've got spade lugs to connect to the front banana jugs. So, we place that back in the housing. So here's the front panel, and you can see how they've got O-rings here. So that'll just fall off. You can see there's diodes, some little, those look like tantalums to me. So, the traces come in there. So I think this is just for some of the connections. But I don't know why this is so much heavier than this, or why they couldn't just use, you know, maybe they were physically isolated on the board. I mean, if you look at this, you do see that some of the connections are at this side and the rest of them are way over here. So maybe it's possible they just couldn't, they didn't have enough board space to bring the traces that were here over to this end. But this is sure a heavy duty connector. Maybe they just used this because they already had one. This is what the line connection also uses. You can see this is a double-sided board. Looks like this is so this is 4.5, I would guess. This is the half. That's kind of amusing. Or this may just be used for determining, you know, signaling sign or something along, you know, positive, negative, jazz like that. Old style resistors. Gold-plated leads. That dates them pretty effectively. This is Rev D apparently, which is pretty impressive. Now here's this back plate, and you can actually see there's separate little shiny sections for the readout and each of the little indicator LEDs. The rest of it is kind of matte. This almost looks like it was sold as a kit. Let's see, so I'm going to put on that upper corner. And this center one, I think. I can just go like that, yeah. So I wonder if this was a kit, because if you look, I mean, you can see that this is not aligned with that and other stuff like that. Pretty decent shape. The matte finish on this doesn't seem to significantly impact the transparency, which is interesting. Anyways, so you can see some other stuff here. You know, these are probably input protection. I forget what they are. These are, you know, spark gaps or metal oxide varistors or something like that. Everything seems to be labeled ABC. That's quite nice. Now, what are these transistors? They are U3108. E. But they're labeled Q. That one, and this one appears has either been replaced or is different, because this one has Hong Kong on it and those don't. That is a FN 3587, I think. The other ones are all U3108s. We've got a big canned device there. That's a 2N3439. I'm not too sure what that is, but it's labeled Q11. That may be a voltage reference, but it's a 2N, which makes me think it isn't. Back here we have old style classic bridge rectifiers in a circular disc can. More film caps. MC1741, 741, so that's a 741 op amp, I think. I guess 803279. Here's a CA3088. I don't know what that is. This looks to all be all logic. Here's a DM74 LO3, 7408, 7400, 3068. That might be 4000. There's a national. Excuse me, I'm sleepy. There's a national semi DM7404. Okay, never mind. That's just more 7400 series logic. So I bet a lot of this is probably display driver. Because, so actually, while I'm at it, so here's the bottom side of the board, and yeah, actually, what you can, first of all, you can see that's quite interesting. So it appears the transformer is always connected, because here's your, basically here's your line input, goes over to the transformer, is always connected. Here's your secondary, comes out, runs to the power switch on the front, and then runs back here. So it appears that the power switch disconnects the secondary of the transformer, not the primary. That's kind of intriguing. You can also see that it looks like some of these range select switches don't have any leads poking out of the bottom, or some of the leads are not poking out of the bottom, which is to prevent creepage. Over here we can see some interesting stuff. Here's a nice little guard ring on the PC board around this little device, and you can see, so what this is you know, basically what they have is they have a high impedance input op amp generally, or you know, it could be a transistor buffer connected to these nodes, and that drives this circular trace. And what happens then is that because the surface of the board is, you know, there's some leak, ergo a little bit of current can flow, this ring is held at exactly the same voltage as these nodes, and the end result is that because they're at the same voltage, there's no net current flow, and because whatever's driving this ring can source some current, you know, any current that would leak from some of these other surrounding traces into this node and, you know, basically cause incorrect readings, just leaks into this guard ring and then is then sunk or sourced from whatever's driving it, which may be this pin here. I'm not sure. You can also see that it looks like whatever's driving this guard ring is also driving the entire shield. So it looks like the shield is held at whatever this potential here is, which is kind of interesting. That's probably to reduce capacitive coupling. Though that seems like, assuming there's some decent spacing there, there shouldn't be much coupling, but I don't know. Trippy. What is that component there? That is that little, where is the label? So that is an LH10022CH. So this is probably an early high performance op amp, I guess. It's labeled QA103. It could also be a matched set of transistors, so I don't think so, because they're not, it's not really big enough. Oh. Oh, I see. So these two are just press to latch, press to unlatch, whereas these four are snaps. And then this is the same for these. You can see sometimes they get a little stiff. There's the input for the battery. And there's just a few little transistors down here, and you can see they've got markings on them, but they are PN PN4355. See if I can't make out this other one. PN4355, PN4355, they look to all be the same. So it wouldn't surprise me if these are driving like the column drivers versus the row drivers for the front panel LEDs. Their proximity and the fact that it looks like a trace from each of them runs into the connector for the front panel makes me think that pretty strongly. You can see it uses actually, what are all of these? So this transistor here is an ITE 4392, 4392, 5139, 3565. So these are all PN4365, PN5139. Lots of little transistors. You can see we have tremor pots, these weird things. Here's another film cap I didn't notice earlier. So these film caps, the way they work is they actually just, it's just literally a roll of like mylar and a little strip of aluminium, and then they have leads poking in to connect to it. So they have 2 strips of aluminium and 2 strips of mylar, and they overlay them, and then they have a lead poking in for each of the strips of, to connect to each of the strips of aluminium, and then they just roll it up. And the end result is you get a very high quality capacitor, but I don't think you can get them in very high capacities, and they're expensive. Anyways, so the low lead clips on there, high lead clips on there. This whole thing kind of sits over like that. Oh, I see how this works. So this can measure DC volts and AC, DC volts, AC volts, DC amps and AC amps. So what happens is if you're on DC and neither of these are pressed in, you're measuring DC amps. Now you're measuring AC amps. Now you're measuring AC volts. Now you're measuring AC milliamps. So I see how this works. So you just kind of pick one, and then the interlocks prevent you from pushing in the amps if you had milliamps pressed down and vice versa. But you can switch between the two. And then I guess if you leave one of these plugged in and switch into ohms, it probably disconnects everything. That's kind of intriguing. And then it looks like we have a little input null down here, which goes into this really long, or this multi-turn pot. And then here are the input fuses. That actually looks like a light bulb. That's an interesting fuse. Look at that. It's got like 2 wires in there. I'll have to look up the datasheet. Fortunately, since this is Keithley and it's old, I'm fairly confident that all of the technical documentation for this is probably freely available. But Keithley's pretty cool about that. So here is this. Oh boy, I gotta take the board out of the casing again. Oh, I see why these leads are set like that. It's so that they can be made to clear some of the internal construction more elegantly. It's because they need to fit around these fuses. Not that they do that well from the feel of it. So then I think I will leave the battery pack out, at least until if and or when I bother to get new parts for it. So these 4 little things just sit over like that. And actually what I think I will do is plug in the AC line, plug the whole circuit in. So I definitely have dirty switches. But it appears to be working. So actually that's a pretty interesting test. Multimeter, so I don't drop stuff everywhere. put this on ohms, put this on DC, and then so first of all, input impedance is, assuming I can make a good connection, 10 mega ohms on the button, and our ohms testing burden voltage is 6.32 volts. So we can do the exact opposite, which is put this on volts, put this on ohms for high, and our burden voltage is, or well, not our burden voltage, our testing voltage is exactly 1 volt. I thought it was 2. Huh. Anyway, so that's, and the input current for this is actually 11 megs. Huh. That's interesting. It's, both of them are reading as 1 volt. So I think maybe you need a smaller resistor for that to work properly. Anyways, seems to work fine. So I'm just going to leave the handle off because it's kind of broken. Pull to rotate. So here's this interesting thing where you can see it's got 4 line voltage input ranges. Let's see if it'll focus. So 90 to 110, 110 to 125, 95 to 235, or 210 to 250. Which is kind of intriguing. So they've got a switch low norm, and then they have a 117, 234 setting. 3 AG, 1/8 amp, internal slow blow used. So these are the line protection, not the other protection. Not the fuses on the inputs. Kind of leaves a big hole, and I'll live with that. That is all set in, isn't it? So here is this interesting kind of instruction panel. So you can see the various accuracy. Plus or minus 0.1%, plus or minus 1 digit, input impedance 10 mega ohms. DC in milliamps, DC in A, 1.1 ohm versus 1. So that'll also tell you something about the, you can compute the burden voltage of that. So 30 milliamps across a, 1 milliamp, 1 kilo ohm is 1 volt. So 30 milliamp, or well, 2 milliamps, the burden voltage is going to be roughly 2 volts at full scale, which is 2 milliamps. Which is pretty, Dave Jones wouldn't like it, but I'll live. Are these going in at all? It feels like it is. You can see 0.0001K, so basically 0.1 ohm to 2 mega ohms, plus or minus 2%, 2 digits, 200 millivolts max, in range. Oh, I see, so we're out of range is what's going on because this meter's 10K. High ohms is 1 ohm to 20 mega ohms, 2 volts max in range. So with 10 megs it looks like the voltage is, with 10 megs the voltage was sorry, I'm distracted by the screw not really screwing in. So 10 megs is, I guess, half of that. So they just use a straight up resistive divider and then just measure the voltage, so that seems kind of strange. Anyways, so we can see that our AC voltage is 0 to 500 volts, 20 hertz to 10 kilohertz. So this may be true RMS, which is nice. I didn't actually look, I didn't really care. It was, it was $29.99 plus $16 shipping, so, I can live with, non-true RMS. Patents pending. So it seems like it flashes 0.17 when it's out of range. Oops. And you can start to see how these switches, so you can see how the switches are kind of dirty. So theoretically, most of these switches are what's called self-wiping, so just toggling them back and forth should make them start working better, simply because what happens is the contacts kind of scrub against each other as you switch them, and the end result is that if there's oxide on them, which is what happens when they're old, kind of the scrubbing action will eventually make them start working properly again, which you can see appears to actually be happening, though it seems like they're still kind of cranky. But you can see already it seems to come up without freaking out too much. So we're in ohms high, ohms low. So the only nice thing is the DC volts and the DC amps just drop down to 0 based on whatever their input impedance is. So just pushing these lights up the amp and the milliamp button. Whereas in ohms, you see we fall into K and then it kicks over to mega ohms and then it goes, wait a minute, nothing's there. Well, that's kind of interesting. So if we put it in volts, it drops to 0, and then if we put it in ohms, it's charging up the capacitance across here, whatever that is, and then if we go back to volts, it drops away. Oops. Go back to volts so you can see the capacitive, whatever it's, the output voltage discharges. That's kind of intriguing. Anyways, so there's a cute little, yeah, so you can see, so it's using that that fifth digit just basically for the negative sign. Other than that, it's basically a 4-digit, 3.5-digit multimeter. But the thing I like about this, and the reason I kind of like this, is it's LED based, because they're much easier to read than LCD based ones. You know, so I can kind of put this up and it lights up and it's self-illuminating. So that'll just kind of live on my bench. Actually, there's a fun test. So let me go over to DC volts. Steal my test leads. These are very crappy test leads, but I'll live. So I wonder if 0.02 volts. Our total stack voltage is 0.11 volts, and it looks like it's discharging just from the load of the meter. I'm not sure how this is wired up internally, actually. It looks like they're just all in series. So then the other interesting thing would be this funky little pack. Oh, hey look, it's got a whole 1.6 volts. So from the look of it, black goes there. Oh, here are the two. Ah. For the guy who complained about the moving stuff around on my bench making a lot of noise, 1, bite me, and 2, I've bought a lapel mic. It's in the mail. I don't have it yet. So this whole stack is 0.295 volts. So this is it's 3.5, because you saw, like when I'm measuring there, we have 4 significant digits. Whereas here it goes over, so we get 0.295, 0.3. So that may just be an effect of the fact that I charged it slightly, by virtue of the fact that I tested it. I was testing it on the battery. I actually wonder if I could possibly try and charge some of these back, though it looks like some of them have been leaking internally. So I mean, these are just size C mic heads. These are easy to track down. This would be slightly more involved, but I don't know if I'll even bother. mean, it's a nice option to have. What I think I'll do is, so fortunately these either haven't leaked or I'm just not able to see the leaking. So I'm going to go with they haven't leaked. This one appears to have leaked out of the wrong end. That's never a good sign. So of course, you know, these are NiCad batteries, so cadmium, wash your hands. Cadmium's like most heavy metals, and it's probably not too worrisome unless you eat it. It's like lead, you know. I mean, they actually, in a lot of mil-spec equipment, they use cadmium-plated connectors because cadmium's an excellent anti-corrosive. But, yeah. NiCads. Fortunately, now we have NiMines, which are more nicer. Anyways, cool. Hope you found that kind of interesting.